Combustion Analysis. The mass amount of each element in a compound can often be found by decomposing the compound into its elements by reacting it with another substance. Hydrocarbons, here's a hydrocarbon, CXHY, can be combusted with oxygen, okay, that's a fire, to determine the mass amounts of carbon and hydrogen. All the carbon will be converted to CO2 and all the hydrogen will be converted to water. This device provides controlled combustion of material, burning it, and then traps the emitted water and carbon dioxide. So we have our oxygen coming in here, and this is a furnace, so it reacts with the sample, and it emits carbon dioxide, water, oxygen, and other gases. The first area here, we have a water absorber, such as magnesium perchlorate. Second one, we have a carbon dioxide absorber, such as sodium hydroxide. Then, what comes out the other side would be oxygen and other gases. Now, if our sample only contains hydrogen and carbon, then the masses of the water and CO2 emitted during combustion is sufficient to determine the empirical formula. If a third element is present, then the original mass of the sample is also needed. The empirical formula is determined by calculating the mass of carbon in carbon dioxide and hydrogen in water, since only carbon and hydrogen comprise the sample. We have 2.461 grams of carbon dioxide. So 1 mole of carbon dioxide is 44 grams of carbon dioxide. Then we have 1 mole of carbon for every 1 mole of carbon dioxide. Right? There's just 1 carbon there. Carry out the division and unit cancellation, and we get 0.05593 moles of carbon. Let's move to water. 1.344 grams of water. 1 mole of water is 18 grams of water, and we have 2 moles, here there's 2 over here, of hydrogen for every mole of water. Carry out the unit conversion and the math, and we get 0.1493 moles of hydrogen. The amount of moles of carbon is less than the amount of moles of hydrogen. Divide the amount of moles of carbon and hydrogen in the products by the amount of moles by carbon. So here's the carbon. So moles of carbon divided by moles of carbon, well, that's just going to be 1. Then moles of hydrogen over the moles of carbon will be 2.67. Our CXHY now becomes C1H267. But fractional subscripts are not acceptable in chemical formulas. The fraction, 2.67, must be multiplied by a small integer to convert the fraction into a whole number. Always start with the number 2. CHXY now becomes C1 2.67, which of course we can't use. So start by multiplying the fraction, 2.67, by 2. We get 5.34. That is not a whole number. So let's try 3. Multiply 2.67 by 3, and we get 8. That is a whole number. So now we have to multiply each subscript over here by 3, right? Whatever we do to one, we have to do to the other. So carbon, 1 times 3 is 3. Hydrogen, 2.67 times 3 is 8. So our empirical formula is C3H8. But what if a third element is present? Then the original mass of the sample will be greater than the masses of the carbon and the hydrogen in the carbon dioxide and water. That mass deficit is ascribed to the third element. In this case, the sample is presumed to consist of carbon, hydrogen, and oxygen. Here's the total mass. Here's the excess oxygen. And here's what we got for carbon dioxide and water through our combustion chamber. Using a similar analysis, we start with the carbon dioxide and water, and 2.91 grams of carbon dioxide is 0.79 grams of carbon. 1.78 grams of water is 0.20 grams of hydrogen. So we have our total mass, right, the left side there, minus the 0.79 grams of carbon, minus the 0.20 grams of hydrogen, and that means we have 0.53 grams of oxygen. Now we do the molar calculations. Here's the carbon, that's 0.066 moles of carbon, And we're going to divide that by 0.033. Why? Well, actually, we didn't show that till the bottom here. Here's the oxygen. The oxygen has the smallest molar concentration. That's 0.033 moles. So there's one oxygen because you divide it by 0.033. With hydrogen, you divide and you get 6 hydrogens. And here with the carbon, you get 2. So our empirical formula is C2H6O.